Morning, everyone. I'm here to talk about predicting shelter occupancy during emergencies, even when movement data is incomplete. This is a critical challenge, especially in crisis, when data gets lost due to network failures, sensor damage, or privacy rules. Today, I'll show how we build a deep learning framework that stays accurate even with 70% of the data missing. Public shelters like bomb shelters, metro stations, or hurricane refuges are key to keeping people safe. Their success depends on predicting demand, but we often have to make these predictions without complete data. Predict too low and we get overcrowding. Predict too high and we waste resources. So the real question is, how do we forecast occupancy when we don't have the full picture? Missing that data isn't just a small problem, it's how things work in reality. GPS signals drop, networks get congested, privacy laws prevent constant tracking, and infrastructure gets damaged. Often we lose more than half of the data we'd expect. Standard deep learning models assume regular, complete data, so they fall apart in these conditions. Our work has three main contributions. First, we designed a new model that combines learnable data imputation, bidirectional LSTMs, and graph-neutral networks. Second, we tested it thoroughly against other methods across different missing data scenarios. Third, we provide uncertainty estimates because emergency teams need to know when they can trust prediction. In short, we track citizens moving between shelters over time. Ideally, we'd have full data, but actually we only get a sparse set with a binary mask showing what's missing. The gaps can be random, linked to observable factors, or not random at all. Our goal is to predict when shelter will exceed 80% capacity using a function that handles incomplete data, captures both time and space patterns, and provides uncertainty. Without uncertainty, operators can't rely on the predictions. Our architecture, SMTD, works in three steps. First, the learnable layer handles missing values using temporal decay, meaning it gradually forgets old information rather than just filling zeros. Second, a bidirectional STM processes each person's movement, capturing patterns despite irregular data. Third, a graph neural network combines individual data into shelter-level predictions, using the relationships between shelters. The key innovation is how we handle missing data. Simple methods like forward fill or averaging create bias, especially during chaotic evacuation periods. Instead, we use a learnable decay factor based on a time since the last observation. This lets the model adapt to different missingness patterns. It learns what to do instead of following fixed rules. We created a realistic simulation using MAT-Sim with 10,000 people, 10 shelters, and 72 hours of activity. We tested four different missingness rates and three patterns: random, linked to speed, and block gaps of 30 minutes. We compared our model to four baselines, including the standard LSTM with forward fill. Our main metric was MAE in hours. Here are our key results. At 10% missingness, all models performed well, but as missingness rose, ours pulled ahead. At 50% missing, a realistic figure, our model scored 2.33 hours MAE compared to 4.87 for the standard LSTM, a 52% improvement. Even at 70% missing, our model stayed useful, while others became unreliable with errors over 7 hours. Random forest worked okay at low missingness, but struggled at high rates because its imputation is fixed. Point estimates aren't enough. Teams need confidence levels. Our model keeps accurate prediction intervals up to 50% missingness, staying close to the target 90% coverage. In contrast, the standard LSTM is dangerously overconfident. At 50% missing, its actual coverage drops to just 67%. That means operators think predictions are more reliable than they really are. Our model tells you when it's unsure. To understand what drives our success, we ran two ablation study at 50% missingness. The full model achieved 2.33 hours MAE. Removing learnable imputation and using forward fill increased the error by 65%, meaning this component alone accounts for about 60% of our gain. Removing the GNN raised error by 46%, showing the special aggregation is essential, not just an add-on. Removing both brought us back to the standard LSTM with double the error. Bidirectional structure helps, but less significantly. We also checked performance across different shelters. Central shelters with more data naturally did better, but the key takeaway is that the GNN helps balance this out when a peripheral shelter has sparse data. It can borrow information from nearby shelters via graph convolutions. Without the GNA, those low traffic shelters would have 4.2 hours error, much worse. So spatial aggregation isn't just helpful, it's essential for fair performance across all shelters. We also looked at missingness patterns. When missingness depends on speed, like faster moving people being more likely to drop out, error rises slightly because we lose data during the most dynamic evacuation phase. Block missing 30-minute complete gaps was the worst, reaching 3.12 hours MAE. This tells us something important. Communication systems should prioritize avoiding long blackouts over reduction random packet loss. A 30-minute gap causes more harm than many random drops. Practically, this helps shelter managers allocate resources proactively without needing constant surveillance. Hourly updates with uncertainty intervals are enough. Our model degrades gracefully as data gets sparser, error rises slowly, and uncertainty widens appropriately. Most importantly, this approach supports privacy regulations. It doesn't require continuous detailed tracking. It works with aggregated or partial data. That's privacy by design, proving that AI for critical infrastructure doesn't have to sacrifice civil liberties. To wrap up, we introduce SMTD, a framework that predicts shelter occupancy reliably even when most movement data is missing. At 50% missingness, we cut error by 52%, compared to standard LSTM and maintain well-calibrated uncertainty. Learnable imputation accounts for 60% of our gain, and the GNN adds another 25%. We acknowledge limitations. Our tests are on synthetic data, and scaling to very large cities needs more work. Future steps include real-world testing with civil protection agencies studying robustness against attacks, exploring federated learning, and adding online learning capabilities. We believe this is necessary to step to move AI from the lab into real-world use, where it can help protect lives during emergencies. Yeah, thank you for listening.